Hi guys, this is the promised cyclohexane ring conformations video, our second installment. There's construction going on outside. I think they're using I don't know, I can't see it, but it sounds like a giant saw or something. So if I stop talking all of a sudden, it might be because that's happening, and I'm not sure you'll be able to hear me over that. So we talked a lot in class yesterday about ring conformations. And we talked about how usually when we're drawing cyclohexane so far, we've only drawn this kind of flat hexagon shape. There's our line bond structure. But that's, a flat 2D image of something that's actually existing in a 3D world. So the model shows you how, even though we think all the carbons are going to be in the same plane based on how we draw them, you can actually see that the carbons are out of plane with the, I don't know if you can hear that, but the saw is happening. Anyway, so you can see that actually 3 of the carbons are on the same level, and then the other 3 are up above them. And then we have our hydrogens all along here. So what I've done is I've color-coded the hydrogens. So currently all the blue ones are in axial positions, and you'll notice that they're alternating up, down, axial. So here we have up axial, up, down, down. And we talked about how you can figure out how to draw those based on the way that the carbons are kind of pointing. So this carbon's going down. That means that the axial position is going to be down. Now the equatorial positions are the white hydrogens. And we talked about how the axial ones are in that up-down situation, the way that the Earth's axis goes up and down through the planet. And then the equator goes around the planet, just like how these hydrogens are equatorial. They're going around the cyclohexane ring. So, and they also alternate up, down. So if you have up axial, you have down equatorial. And if you have down axial, you have up equatorial. So the cool thing about cyclohexanes, I don't know if you can see the chair. I'm not good at lining up with the camera here. Here's our chair conformation. The cool thing about cyclohexanes is that they're constantly moving, right? They can go through that unfavorable boat conformation that we talked about. Here are those flagpole interactions where you have these two groups trying to end up in the same place. But we can actually go through a chair flip, where now I'm actually in the opposite chair from what we had before. And now the white hydrogens are all in the axial positions, and the blue ones are in equatorial. So this is happening all the time. So remember, molecules aren't just staying put, they're constantly moving. There's free rotation around sigma bonds. The rotation in a cyclohexane is a little bit limited though, because we're tied up in a ring here. So there's not that much rotating they can do without breaking the cyclohexane open, and then you would have totally free rotation. But since we don't, there's just a couple of things that it can do. It's going to be moving all the time. It's going to go from chair to boat to chair to other chair. And so the question really is just, where is it spending more of its time? Is it trying to stay here in this boat conformation where you have these flagpole interactions and then you have all these eclipsing hydrogens? If you remember when we were talking about Newman projections, we said that eclipsed conformations are going to be much less favorable, and you can see that this entire thing is eclipsed, so that's not ideal. Or is it going to be in the chair conformation where every single carbon is staggered? Hopefully that kind of pointed question tells you what the answer is. The answer is, of course, we prefer the staggered conformation, and so that's why chair is going to be the favorable position. We also discussed how groups that are substituting hydrogens are going to want to be in the equatorial position. We looked at 2 different examples. We looked at 1,2 dimethyl cyclohexane, and we said that when those methyl groups are in the cis position, meaning both pointing up or both pointing down, one is going to be forced to be in the axial position, and the other one gets to be in the equatorial position. And I say gets to be because when they're in the axial position, this methyl group, which is much larger than this stick model actually makes it look like, is trying to interact in the same space as these hydrogen groups. And if you really start substituting the cyclohexane, you're going to have a lot of those diaxial interactions that are going to be unfavorable. And then if you do a chair flip, that one that we just had in the axial position is now in the equatorial, and the other one is in the up axial position. So they're just going to keep trading positions between axial and equatorial. But if we make it trans-substituted, if it's trans-substituted, meaning one group is up and one group is down, they can either both be axial, which is something you could do if you wanted, or they could both be in a happier equatorial position. Look how much space they have when they're in equatorial. They're staggered from each other. They're going out away from the ring. So that's going to be a really great thing. Whereas if they're both in axial positions, they're going to be both suffering from those diaxial interactions. So that's why we're going to prefer to get as much as we possibly can in the equatorial position. When we get back to class, we'll talk a little bit about different substitutions. This is only talking about 1, 2 so far. But don't worry, we'll do more. So I hope this helped. You can always come to my office and play with models yourself if you would like. So I'll see you guys on Tuesday.